It's 10 o'clock, so it's time to start. Thank you, everybody, for coming to this thesis defense by Tyler McMaken. Tyler is a graduate student in the physics department, but he has an enormous connection with the astrophysics department. I'm his advisor, Andrew Hamilton, and thank you to the rest of the members of the committee, Jason Dexter, Oliver DeWolf, Paul Romashkian, and Andy Lucas. So prepare to be a combination of impressed and baffled. Tyler, go ahead.
Yeah, thanks. Thanks. Well, welcome. I'm glad that you all could come here today and hear about all the things that I've been doing inside of black holes. So I'm going to start out by just mentioning that we have a broad audience here today, and so I want to be as pedagogical as possible in my presentation. But I also realized as I was preparing that I'm condensing 6 first author works into a single presentation, which is never a good idea. So I hope that you'll forgive me if I rush through things a bit fast, but please do feel free to stop me if there's anything that I don't really explain fully. And hopefully it's all unified under one common theme. And that theme is to answer this research question of what happens if you fall into an astronomically realistic black hole. And so to answer this, we're going to split this talk into 2 parts. The first is going to be using the framework of classical gravity. So this is using Einstein's general relativity theory that describes gravity on large scales. And you can make a bunch of predictions about geodesics and visualizations and cool stuff like that. And then the second half of the talk will focus on what quantum mechanics can tell us about gravity. So this will be under a framework called semiclassical gravity, of how gravity behaves on a quantum level, at least to first order. So the first thing I want to just get out of the way right away is the most common question that I hear asked is this actually physics? And why should we care in the first place about what happens inside black holes? I mean, by definition, black holes are things that you can't escape. You can never see anything inside of it. So are we actually predicting anything we can observe? And it turns out that you can. And so we're trying in this thesis to come up with a theory which is not just mathematical, but is also physical. We're trying to map this to realistic systems that have rotation and accretion and all these other things that we observe in astronomy. And also, when you take quantum mechanics into account, it turns out that things can escape black holes. This is what Hawking radiation is, and so we'll see exactly what that is. And usually it's too small for you to actually see from Earth or anything like that. But it can have profound implications for what you would see falling in. And this instability that we're going to talk about inside a black hole can completely change the geometry of the black hole and even change the external parameters that you might be able to observe, like the spin or the mass function. Okay, so with that, let's start out and talk about some classical physics. And the starting point is the simplest model of black hole that we have, the Schwarzschild solution. So this was a solution that was come up with by a guy named Karl Schwarzschild, the guy with the epic mustache right there. So he was trying to find a solution to Einstein's equations of general relativity that he had just come up with. And the solution that he came up with is the following, the space-time line element that you see here. So in general relativity, time and space form one unified manifold. And usually we describe that with a line element, which is nothing more than Pythagorean's theorem. So it's a way of encoding how distances are measured in your space. And so if you have just a flat space, then this would say that ds squared is dx squared plus dy squared plus dz squared. But now that we have this black hole, we see there's this extra function right here that acts in time and space in this various way. It's called the horizon function. And for the Schwarzschild black hole, it takes this form, and we can see it plotted right here. So you can think of this as a gravitational potential of sorts. So if you're starting out at some large radius, you can fall in and eventually reach the center of the black hole. And the point where this horizon function crosses 0, the root of the horizon function, is the event horizon. So this is the point of no return. You can visualize a black hole also as space flowing inward, kind of like a whirlpool. And if you do that, then the horizon is the position where space starts falling faster than the speed of light. And so if you are within this position, then there's no way you can escape back out of the horizon because you can't go faster than light yourself. And so you're doomed to reach the singularity. And if you're curious, this bird did make it out okay. Okay, so these are the ways that we can visualize black holes in general. You can plot the horizon function, you can draw these animations, but usually scientists don't like drawing animations if you're publishing papers, things like that. So there's a better way of visualizing black holes that keeps track of both information about space and time. These are called Penrose diagrams. And raise your hands if you're comfortable with Penrose diagrams. Probably not a lot of you. Okay, so about roughly half of you. That's more than I expected. That's great. So let's just go through briefly what we should know from these diagrams. So they're plotting space and time. And the key thing that Penrose did was two things, actually. The first was we have an infinite space here. We want to crunch that down into a finite space. So infinity is at a finite point here on these Penrose diagrams. And the second thing is that light rays are always drawn with a slope of plus or minus 1. Plus 1 if they're going outwards, and minus 1 if they're going inwards. And so this is just a flat space-time. You can see a light ray comes in, it bounces off of the origin because we're only plotting positive radius, and then continues off like that. What would a black hole look like? Well, it would be something like this. So we have our normal universe, just like usual with infinity out here. But this light ray now, instead of going through the origin and then coming back out to infinity, is now going to reach r equals 0. And that's the end of its journey. And so any point past this line right here, which we call the event horizon, is a point of no return. Because if you are inside of this black hole, then there's no way that you can return to the universe that you came from. So this is a Schwarzschild black hole. It turns out that for quite a while, people didn't really believe that this had any physical meaning. Einstein himself, for several decades, didn't really think that this was worth studying or that it corresponded to anything in reality. And one of the reasons for that was because this is an eternal black hole. So it has existed for all time. And you can see here, there's this surface right here that is technically a white hole horizon. So if you look infinitely far into the past, there is not our normal universe you see. There's still this black hole, white hole analytic solution that you can find. So it wasn't until a few decades later that people were finally able to connect this to the physical reality that we live in. And one of those people was the father of the atomic bomb, Oppenheimer, who with his student came up with this model that has this red line right here is a collapsing shell of matter that mimics a star that might collapse to form a black hole. And so now we have this model that we can see that stars actually can form black holes, and that they do actually correspond to things that we see in the real universe. So in everything that follows, I'm not going to be using this Oppenheimer-Schneider model directly. Instead, we're going to use these eternal spacetimes, which is an appropriate choice as long as we take the collapsing star to have occurred far enough into the past and then apply the appropriate boundary conditions at that past horizon. Okay, so let us see how we can visualize this. So there's this code, the black hole flight simulator, that my advisor, Andrew Hamilton, had developed a few decades ago that is absolutely amazing. You can ray trace in real time to show you what Einstein's equations would predict you would see if you were to fall into a black hole or fly around or throw something else into it. There's a bunch of different things you can do. So we'll see exactly what happens when we fall into this Schwarzschild black hole right here. You notice there is a shadow of the black hole where light is bending around it. And we can also follow along Penrose diagram or just a slice of what it looks like in space. Right, so we're going to start out at a few hundred gravitational radii away. This is about 17 AU if we were considering the black hole at the center of our galaxy. So that is roughly the distance of the closest star that we've ever observed that has come to Sagittarius star. But that's not really as relevant. So let's just see what happens. Ah, I did optimize, and I am regretting optimizing. Okay, let's hope that this works. We're about to cross the event horizon here. Ha, nothing special has happened. We can still see that black hole shadow in front of us that is growing over time. So let's tilt our view a little bit so we can just see that horizon in front of us, which is not the event horizon. Now we're really slowing down time. So we're in the last fraction of a second. We can see that the entire sky above us is squashing down and forming just an infinite plane and getting highly redshifted until, let's stop it right there. We basically hit the singularity. So when you reach the inside of a black hole and you land on that singularity, you don't reach a single point. The singularity is not just a single point. It's actually this infinite plane from this view that you can see in all directions. So it is a space-like singularity, which means that it's unavoidable. And no matter how you fall in, each spot you're always going to land on that singularity at some point in time. You can never steer away to avoid it. Okay, I'll point out that this sort of simulation was pretty easy for me to record on my own laptop. It took like a few minutes or however long it took to actually play that. NASA recently released a simulation that's basically identical to this, except for they also painted an accretion disk on top of it. And they made a huge deal out of it. They're like, scientists simulate black holes for the first time inside. And it took multiple weeks on all these supercomputers. But so hopefully this becomes more known to the public over time, but yeah. Okay, so that is a Schwarzschild black hole. It's a great solution, but we want to go beyond that. So there are a few things that we might want to do that generalizes from the Schwarzschild solution. So here is just normal spherically symmetric black hole. But in reality, black holes don't look like that. They actually might look something like this. So if you add rotation to a system, most objects in the universe have angular momentum, then that'll change what your space-time looks like. And in actuality, black holes don't just look like that. They might look something like this. So black holes are surrounded by accretion disks with highly energized plasmas and all sorts of jets and weird things that we might want to understand. And many of these people in this room are trying to simulate and understand. So I'm not going to be dealing directly with the geometries of accretion disks, but we will go through how rotation and accretion affects the interior geometry. So let's start with rotation. The simplest model for a rotating black hole was first developed in 1963 by Kerr, and he found this line element. It's a bit more complicated, but we can see some of the same structures. So there's a horizon function here that looks like this. And so the main difference in this horizon function, so there's this parameter A that measures the spin of the black hole. And now there's not only one horizon, but there's actually a second horizon where the root of this horizon function. And this we're going to call the inner horizon. It also gets called the Cauchy horizon. And you can think of this, if you're picturing space as flowing inward, the event horizon or the outer horizon is where it starts flowing faster than light. The inner horizon is where it once again slows down to slower than the speed of light. You could think of this as the rotation of the space-time is causing a centrifugal force that's flinging you outward. So you can't actually reach to the very center. And the point at which you're prevented from doing that, where you start to slow down slower than light again, is this inner horizon. You can also draw a Penrose diagram, and we can see a bit more structure that we'll analyze in a bit. So there's a universe, black hole, and then the inner horizon gets split into these two sections here. And beyond it, you can see that our origin, r equals 0, is now no longer space-like, but it's now time-like. So this is something that you can avoid. You can just steer around it. But then the question is, what happens beyond that? We have a singularity, and so the equations break down. So we might want to know what that is. Okay, so yeah, just once again, there's the event horizon, and there's the inner horizon. And let's see what it looks like if you fall into a black hole with an inner horizon as well. So we do not have simulations currently for the Kerr spacetime, but we do have a proxy for that, the Reissner-Nordstrom spacetime, which is a black hole with an electric charge that has many of the same causal properties as Kerr because it has this inner horizon. So in the words of John Wheeler, charge is a poor man's angular momentum. The way that we're going to go about this, I've plotted basically the whole 4-pi view of your sky here. So if you're looking directly downward at the black hole, that's the left half of the image. The right half of the image is looking directly upward at the sky above. And I've also just want to show this navigation panel. So we have you, your flight path, the outer horizon, the event horizon is the red one. The inner horizon is this salmon color. And let's see what happens. Okay, so I've started it. We're starting off pretty slow, but slowly we'll pick up speed as we fall inward. So we can see right away, if you look at the right half, that the sky above you is redshifted. This is a general result from general relativity. The sky below you is just a little bit blue shifted. And as we come in, then eventually we're going to cross the event horizon. And the same thing that happened before will happen, which is that we don't actually notice anything special. The event horizon isn't a locally observable surface. Now let's see what happens when we reach the inner horizon. Okay, a bunch of weird stuff has happened. Now we're in this new region. This is actually a white hole. And now we've escaped it. And you'll see we're in a new universe. I've shown it as the same universe. You can do some topological things. But now we're just going outwards. And if you look in front of you, you'll see that this white hole that we escaped from shrinks as we go into our new universe. So this is a pretty neat animation, but I want to show you just once again that something weird happened at the inner horizon. If you notice, there were some flashes, there was some weird stuff. So let's analyze that. And the really weird thing that happened, which leads us into our discussion of accretion, is that something that Roger Penrose was the first to point out back in the 60s, which is that the inner horizon is a surface of infinite blue shift. So he pointed this out in this work, which is not on the internet, but it is in the library at the top of the Gamma Tower. So what he means by that is that if you were to fall into a black hole, follow this yellow line, for example, and then your buddy didn't want to fall into a black hole, so they just hang out outside like a normal person, then they could send you light signals. And when they do so, let's say they're sending you light signals at equal periods of time, then as they reach their infinite future, you're going to be reaching the inner horizon. And you're going to do so in a finite time, but they're going to reach the infinite future in an infinite amount of time. So what that means is as you reach that inner horizon and cross it, you are receiving an infinite amount of light from the infinite future. You're seeing the entire end of the universe, essentially. So obviously, this can't be good. Something bad is going to happen. And the thing that happens was first found in 1990. Werner Israel and his grad student, Eric Poisson, found that the full nonlinear solution was something called mass inflation. The idea that if you have any perturbations of a black hole, then they're going to blow up exponentially and diverge at the inner horizon. And so even just a single photon that you throw into the black hole will have a gravity of its own. Yes, photons have gravity because they have energy, and that gravity will end up diverging and causing a space-time to form a singularity at the inner horizon. It's called the mass inflation instability because they were analyzing this model where the mass parameter is allowed to vary over time to account for accretion. So you have non-zero m dot, And when you do this, then you find that M diverges exponentially at the inner horizon. So the external mass that you would measure from outside is still going to be finite, but as you go in is where you notice this instability. So this requires a few different ingredients. You need non-zero surface gravity at the inner horizon, but mainly you need ingoing radiation, and you also need outgoing radiation, which could come, say, from the collapsing star, which formed the black hole in the first place. But when you have that, these streams of matter will inflate through each other and will completely change the space-time after that. And so the question becomes, well, what happens beyond that? So what happens is has been a really tough thing to analyze. A lot of people have attempted over the years to figure out what happens. And one great model was first developed by my advisor about a decade ago. And it assumed a few different things. So first of all, we have axial symmetry. And second, we have conformal separability of the Hamilton-Jacobi equations and a few other technical mathematical things. But mainly, the idea is that you have a constant source of accretion. So some material which is really tiny, but is constant over time. And so if you add that to your black hole, then you come up with a solution, which the equation is a bit too long to include on this slide and wouldn't be really meaningful. But what I found when I started my PhD is that locally at the inner horizon, this solution simplifies a lot. So much that we can actually do calculations with it, which is much tougher when you have this full solution. So this metric I've called the Inflationary Kasner metric. And here is what it looks like. So it's a completely homogeneous space-time, and it's caused by this evolution of this time parameter t that starts from 1, where you are in a regime where space-time still looks like the Kerr metric, say around here, and then t decreases over time to 0. And as it decreases, you can see the initiation of mass inflation. But then there is the second epoch, the collapse epoch, where the space-time bounces and collapses into a space-like singularity. So what do I mean by that? Well, there are these scale factors here, A1 and A2. They measure how much you're being stretched in the radial and the transverse directions. You've probably heard that if you fall into a black hole, you get spaghettified by these forces. That's actually only true in a Schwarzschild black hole. So if you have an inner horizon, then the opposite actually happens. So you might start out being stretched, but eventually, because the inner horizon is the surface where the inflow of space slows down again, then you'll actually get squashed down like a pancake, or you'll get pancakeified. So this is generally what we would expect for like a Kerr black hole, is that you would get squashed. But what this inflationary Kasner solution says is that initially, your radial scale factor is going to decrease, so you'll get squashed down in that direction. But after this bounce, it's going to start to increase. So you'll get stretched in the radial direction and squashed in the transverse directions, which is exactly what we would expect for spaghettification. And so the end result is that once again, you will get spaghettified. Okay, so this is the general form of this inflationary Kasner solution. So you can do things like ray trace geodesics, which I don't want to go into too much. So let me just show the conclusions of this first half then, which is that there are two different effects that we care about. First of all, you want to model the rotation of a black hole. So this generally gives rise to an inner horizon that could be modeled, say, by the Kerr metric. But the Kerr metric has a problem, and that is when you add accretion, then the perturbations from that accretion cause an instability of that inner horizon, cause all of the matter to diverge in energy density and curvature at the inner horizon. And the result of this, if you have a full globally self-consistent solution, that the inflationary Kasner model takes over. So the conclusion of the matter is that the inner horizon collapses into a strong space-like singularity. And so now we do have a model that looks like Kerr everywhere on the outside, but on the inside, then basically looks a lot more like the Schwarzschild solution. Okay, so at this point, I want to pause and take any questions, and then we'll continue on with quantum gravity.
know you were talking about Schwarzschild black hole as a proxy for the rotating picture. Is your work here that you're describing was in terms of Reissner-Nordstrom?
Yeah, that's a good question. So the simulation was in Reissner-Nordstrom, but the inflationary Kasner solution and all of that was for rotating, for starting with the Kerr solution. Yeah. So I've done both, but I think the Kerr is a bit more meaningful. Yeah. What is a white hole? So I guess it's the opposite of a black hole. So it's a region where space is flowing outward at faster than the speed of light. And so if you're inside of it, you inevitably have to escape. So you can never go back in. So on this Penrose diagram, it would be right here if it were to exist, and then you would go into the normal universe. So nobody's ever actually observed one, so they probably don't exist. Okay, I guess you're eager to hear about quantum gravity. So I guess we should go on to that and make like a Marvel movie and add the word quantum to everything. So the questions we want to ask of how to go forward with this is, what if the black hole isn't accreting anything? So this instability required accretion of at least some form. So could we simulate some black hole in the lab in the far future that is completely isolated and avoids this instability so that we can create a wormhole of our own? Or we could also ask, what about quantum effects? So this is entirely classical, but once we get to high enough energy, then quantum mechanics starts to take over, and we haven't talked about that yet. So let us talk about that. The next two slides are a bit math heavy, so I apologize in advance, but we'll get through it soon. The common thing that I hear said, repeated a lot, is that gravity is incompatible with quantum mechanics. And I think this is a myth which was first started around the 1950s and 60s when it was actually true, when we didn't really have a good way of dealing with quantum gravity and this effective field theory framework. But eventually people did work out all of these kinks and add all of the appropriate gauge fixing terms and ghost fields that you need to add. And so now I would say that you can formulate a theory of gravity that is consistent with observations and should predict new observations moving forward. So what is this theory? Well, if you have a metric, then you can split it up into a background metric, G bar, plus some fluctuation on top of that. And this fluctuation, we have a background field. In the classical case, it's a gravitational wave, but in the quantum case, we can call it a graviton, a quantum of gravity. And then you can do all of the, so you can add a quantum field on top of your metric. You can do all of the things that you do in quantum field theory that you learn about in your class. You can write down a Feynman propagator. You can draw Feynman diagrams and things like this. This was a Halloween some year, I forget. This is a penguin diagram, yeah. I was a penguin for Halloween. But we're actually not going to do anything this complicated. The only thing that we care about is one loop diagrams. So these are the so-called self-energy of a field. And if we're only dealing with one loop, then since it's an effective theory, it should be valid up to about 10 to the 19 GeV, which is a very high energy. So the Large Hadron Collider is at least, it's many, many orders of magnitude below that. And so the highest energy cosmic ray we've ever observed is only 10 to the 11 GeV. And so we should expect that this should be completely valid for anything that we would deal with in the real world. And there are two diagrams that are important. One is the loop of a graviton, and one is the loop of a matter field that you might couple to gravity. And it turns out that they are both equally important. They both contribute at the same level and order. And so for the high energy folks who are out there, I feel like I'm obligated to write down an action. Here you go. Because we are only dealing with, or because these are both equal contributions, then what that means is that we can treat the graviton as just a source of matter instead of a source of gravity or curvature, which is what it was originally. And so in what follows, we're not going to deal with the actual graviton. Instead, we are going to construct what's called a one-loop effective action that I'm not going to go into the details of. But we're going to focus on the simple case where you have a scalar field that is free and is coupled to gravity with this coupling parameter c that will basically just take to 0 because that's the minimally coupled case, and it can have a mass if you want. Right, now from this action, you can do the usual things with the least action principle. If you vary it with respect to the metric, you get the semiclassical Einstein equations. So the left-hand side is the Einstein tensor, but then the right-hand side is this new thing, a renormalized version of or a quantum version of the stress energy tensor that you would normally have in general relativity. And if you vary the action with respect to the field phi, then you'll end up getting the Klein-Gordon wave equation. And this, in the non-relativistic limit, this reduces to the Schrödinger equation with a gravitational Newtonian potential. And for a spin 1 field, this would be the Maxwell equation. So spin 1 is a photon. Sorry?
Psi in there.
Yes, so the psi I'm writing is just the state of the field. You can call it anything you want. So usually we'll just stick to a vacuum state, and so I'll put a 0 in here, but it's just an arbitrary state, yeah. That's right, yeah, so it could be the state of phi together with gravity, yeah. Okay, so these are the equations that we can deal with. I'll mention there's this box operator here that is called the D'Alembert. It's just a contraction of 2 covariant derivatives. All right, now let's use this model to do physics. So inflationary Kasner is the thing that we want to deal with. So again, here's the metric that we have at our disposal. And what we want to do, the usual thing you do in quantum field theory, is to decompose your field into a set of modes, just a superposition of particles and antiparticles in equal amounts, given by creation and annihilation operators. And when you do this plane wave decomposition, then we can now calculate different things. So let's focus on the calculation of the vacuum polarization. So this is the expectation value of phi squared. It tells you about quantum fluctuations and the variance of the field and all of that. And it's given by the integral of these field modes, psi sub k squared. So how do we find these field modes? Well, we can use the Klein-Gordon equation. And for this particular space-time, it ends up looking like this. It's a second-order differential equation, which is quite nasty, but actually simpler than you might think. So in some limits, it reduces to a Bessel equation, but in general, it has to be solved numerically. So I did that. I solved it numerically, and I found a value for the vacuum fluctuations, and it ends up being infinity. Now you might say, okay, maybe that's okay. We're inside of a black hole. Things are diverging. But it turns out that this isn't just a problem with being inside of a black hole. There's an infinity everywhere. And it's actually not unexpected to see an infinity. So I'm a musician. I like to think of things in terms of vibrations, and it is helpful with this analogy, I would say. So if you pluck a string, you might know that that string vibrates with a bunch of different oscillations with different frequencies. And those various modes that you could come up with of different frequencies are called harmonics. There's an infinite series of them, and they increase in frequency, but they also decay in amplitude as you get higher. So if you pluck a string, you don't hear an infinite pitch because the modes that are higher up are very small in amplitude. So what if we were to make this system quantum? Well, Heisenberg's uncertainty principle would tell us that we can't actually measure the momentum or the energy of a system precisely. There's always some minimum energy that you're going to be left with associated with quantum fluctuations. We can call this the 0-point energy. And every single mode is going to have that minimum energy. So what this means is that if we're summing up the total energy of our system, each mode is going to have this constant term associated with these quantum fluctuations. And if you sum an infinite series of constants, you get infinity. But we know if we pluck a string, you don't actually create infinite energy. That would be ridiculous. And so what gives? And so essentially, the idea is that not only is the string producing this infinite energy, but your pick also has this 0-point energy. And your eardrums also have quantum fluctuations with the 0-point energy. And it turns out we only really measure differences in energy, not an absolute energy. And so it's clear what we have to do. We need to measure the difference in energy. And so in traditional quantum field theory classes, we learn how to do this. It's called renormalization. And in flat spacetime, it's simple. There's this process called normal ordering that you can go through. In curved spacetimes, it's a bit more complicated. And the reason for that is because there's no uniformly recognized vacuum. There's no unique vacuum states in different spots of a curved spacetime. If I'm far away from a black hole, my 0-point energy is going to look different than somebody who's close by it or falling into it near the inner horizon. And so since there's no unique thing to subtract off, then it's not really clear how you can proceed with this normal ordering technique. But it turns out that there are other types of renormalization. One is called point splitting, is the main one that gets used because there is this unique structure of the 2-point function, which is present in every curved spacetime. So I've implemented this. I used a technique called adiabatic regularization, where you're essentially subtracting off a WKB expansion of the modes so that the result ends up being finite. And there's a bunch of numerical work. So if we are integrating over K space, then this diagram on the left here is the integrand. And we basically want to find the volume under this curve. And so I implemented some adaptive mesh refinement techniques to help me to do that. And then took this cutoff parameter lambda as high as I could go until it eventually flattened out at some value. And then I could find the renormalized value of phi squared for this spacetime. So when I do that, what did we find? Well, each point here, which was found from one of those integrals, is in this spacetime, this diagram. You can see here that there are these two regimes that we were focusing on. So there's the inflation regime and then collapse. So at first, the fluctuations start out at 0. This is just the vacuum state that we're starting in. But eventually, you can see that it increases and diverges as you go to t equals 0. And this happens to follow the same structure as the stress energy in the classical case itself. So what that means is that the contributions from the quantum field actually act to support the already existing classical solution that we had. And so it's not like the quantum field is fighting against this instability. Instead, any quantum flux which is produced is just going to increase the amount that it's going to collapse and amplify it, if anything. So this is the general conclusion. You can also see in this plot that if you increase the accretion rate or you increase the amount that the black hole is spinning, that tends to decrease the amount of vacuum fluctuations. All right, so this is the general picture for this phi squared, but phi squared itself doesn't really tell you much. It's really just a proxy for quantity, the renormalized stress energy tensor, T mu nu here, which was the thing which directly feeds back into the field equations that I had shown you earlier. And so this is the thing that can tell us how much gravity something produces in a quantum field. And so the stress energy tensor is built out of derivatives of that 2-point function. Here we're going to use a slightly different mode decomposition. So instead of K modes, we're going to decompose into omega LM modes. And when I do that, I can do the same sort of integral and subtract off. So each of these points here required summing over an infinite space and doing integrals. And the general result is that T mu nu is non-zero at basically every spin of the black hole that I give it. And in these coordinates, these are coordinates that diverge at the inner horizon. And so if T mu nu is non-zero there, it really means that if you were to pass through the inner horizon, then T mu nu would diverge in regular coordinates. So just keep that in mind, is that as long as this quantity is not 0, that means that you have an infinite amount of energy. So you can also do this for a larger parameter space than I did. So you have spin, but you can also do it for different polar angles or latitudes along the black hole. Previously, there was one study that had done this at a spin of 0.8. I extended that and I did it for everything. So there's what it looks like. It's a pretty good result. And I think that's about all that I want to say about that. But I want to go on to talk about the last topic, which we haven't really mentioned yet, which is Hawking radiation. So Hawking radiation is the first semi-classical quantity that we came into contact with as scientists. And the basic idea that Hawking found in 1974, exactly 50 years ago, was that if you were to send a signal from the infinite past and then propagate it to the infinite future, so say you have some observer who's going to send a signal from here, and then you have somebody else on the other side who's going to observe the signal, then you want to know what they detect. And so you can do so with the help of this Klein-Gordon equation. That'll help you propagate the signal over time. But this is only with a flat space-time. Really what Hawking considered was a black hole. And so it would look something like this. You have your collapsing shell of matter, this red curve, that comes in and forms a black hole. And you want to send a light signal, or just information about your quantum field, in such a way that it escapes just as the black hole is forming. And when it does so, you'll notice it gets redshifted, and it does so exponentially. And the signal ends up being different from the beginning and the end. And this signals that there's particle creation happening as a result of that. So as the wave gets redshifted, it loses energy. Energy has to be conserved, and so that extra energy comes in the form of particles, radiation that's detected at infinity. So Hawking did some math. He wanted to calculate the vacuum expectation value of the number operator, which is built out of these creation and annihilation operators. And when you go through the math, you end up finding that the number of particles follows a black body spectrum. And the spectrum is basically given by a temperature called the surface gravity, which is nothing more than the slope of your horizon function at the event horizon. So this is just the form of this black body. I've included this transmission coefficient here that Hawking didn't really care too much about because he was only considering the high frequency limit, but later on some people did some numerical work to find it and created so-called gray body corrections to it. And I did the same thing. So you can calculate these spectra for basically any point in the space-time, not just people all the way at infinity. So when I did that, here's what I found. Yeah.
Made the animation.
Oh, I made this. Yeah, I think they're pretty cool. Right, so here's what the Hawking spectrum looks like at infinity. So this is an already known result. This is for a Kerr black hole of different spins. And we can see if we plot frequency as over the number of particles, or really the luminosity of radiation, then we'll see it looks essentially like a black body. The dashed curve is an exact black body, so we can see there's a bit of a difference that's caused by the fact that not all of the rays actually reach infinity. Some of them get scattered off and fall into the black hole. But what if we are at a different spot? So if we are at the event horizon, then you can do the same sort of scattering problem, and you find the following spectrum. So it again looks almost like a black body, but there are some gray body corrections. Still nothing too out of the ordinary here. Everything is still behaving as we might expect it to. But now let's look at the inner horizon. So at the inner horizon, when you do the same scattering procedure, you see that things start to get kind of crazy. So the dashed lines indicate that your black body would have a negative temperature, which essentially means that the spectrum is ultraviolet divergent. It turns out when you do the full numerical thing, they don't actually diverge in that ultraviolet limit, but you can see that the luminosity is much higher than in the case of the radiation you would see from infinity. And you can do the same thing at the other horizon, the other inner horizon. So it's split up in two, if you recall, and you get a similar sort of result. So again, at higher spins, just as we saw with the stress energy, the general amount of radiation decreases. And this is the conclusion of that matter. But we might want to do better than this, because this only really works at these horizons. So it's a lot harder to calculate a full spectrum if you are just at an arbitrary position. And so instead, we have implemented a framework that was developed in the last decade or so to calculate an effective Hawking temperature. And I don't want to go through the details too much, but the basic idea is that you have boundary conditions at the past, and you could treat these as an emitter, somebody who's emitting a signal that reaches an observer, which is just falling into a black hole. And the ratio of the frequency detected by the observer to that sent by the emitter will tell you information about the effective temperature. And in the limit that the temperature is sufficiently adiabatic, there's this specific condition, then this reproduces the exact Hawking effect that we expect at infinity. So with this framework, it's nice. It doesn't really require much numerical work. It can be done entirely analytically, and you get this result. So for a Kerr black hole, in general, the temperature, let's look at this plot right here. We can see that as R goes to infinity, the temperature, the red one, tends to go to a constant value. This is the normal Hawking temperature at infinity. But as you fall into the black hole, that temperature increases ever so slightly before then decreasing. The dashed lines are negative because we're on a log plot. And so it continues to decrease until it reaches negative infinity at this point, which is the inner horizon. So I'm just focusing on the red one for now. So this is the radiation that you would see if you're looking downward directly at the black hole. But you can also do the same thing for the radiation seen from the sky above you. Hawking didn't really have that because he was considering observers at infinity. But in general, your space-time around you in every direction is curved and should produce some sort of particles from that quantum field. And so we can calculate it. Now we can go one step farther here. So we've said that the amount of Hawking radiation diverges at the inner horizon. So what about the inflationary Kasner solution? Oh, and I guess I should say it diverges as 1 over the horizon separation distance. So if I include the inflationary Kasner, then it might look like this. So again, we have our 2 stages, inflation and then collapse. And we can see that the temperature turns around again, but then eventually diverges to positive infinity once you reach the space-like singularity in the inflationary Kasner model. So this is the general picture that we have. Hawking radiation diverges, at least in the radial direction, once you reach the inner horizon. And this is in the absence of any accretion. So even if your space-time is completely empty, your black hole is completely isolated, even the mere presence of a quantum field that is initially empty in a vacuum state will cause particles to be created that are going to diverge at the inner horizon. So we should expect that inner horizons probably don't form then, because you're going to have this wall of infinite energy that is created. Okay, so just a few more things. I want to go beyond just this radial temperature, because it turns out you can do this in any direction you look in the sky. So for Kerr, the general result is that for a zero angular momentum observer, then the effective temperature diverges in every direction you look in your field of view. But this is observer dependent. So Hawking radiation is an observer dependent phenomenon. And so for a different class of observers, it only diverges along these radial directions that you can see in this plot on the left, that it goes to positive infinity behind you and negative infinity in front of you, or that actually might be switched. But the general idea is that you have these points of light that you can see with infinite temperature, but then everywhere else is relatively normal by comparison. But what I've shown in this work is that as you are going inwards, starting out at the event horizon and then climbing toward the inner horizon, that if you look in, say, 3 different directions given by these 3 curves, that there always will be at least one direction you look where the temperature does diverge. And so this instability does happen in just about any model that you throw at it. Okay, so I could show you more plots, but I figured the best way to do this would be with another simulation.
To clarify.
Yeah.
So this effective temperature is not the same thing as full quantum calculations that you showed in the previous slide.
That's right. The effective temperature is not the same as the full numerical calculation that you can come up with on the slide before that.
Presumably, the previous slide is see an infinite amount of Hawking radiation as opposed to the temperature calculation.
Right, and they should agree in the if the temperature is adiabatic. And so one of the things that I had shown was that this temperature actually is adiabatic in this limit as you go to the event horizon. The blue one, not so much, but at least the radiation you see from the horizon is. So let's actually see what this looks like then. So same sort of thing as before. We're going to fall into the black hole, see what happens when we come out the other side. Except for now, I'm going to turn on Hawking radiation. So the first thing that we can notice is that there's this limb brightening effect. The Hawking temperature increases generally as you approach the edge of the black hole shadow and is the smallest at the center. My apologies in advance. There's a lot of numerical work that goes into this, so it's kind of choppy, but you'll notice that eventually the inside becomes negative temperature. It's kind of hard to show exactly what that looks like, but I've colored that blue. And eventually that grows to take over the whole black hole shadow. And as you keep going, that just keeps getting brighter and brighter over time and more uniform until eventually it diverges at the horizon. And beyond that, we get this wormhole that we now know can't actually happen because we've reached this infinite wall of energy at the inner horizon. Then we bounce backward. We can see we're escaping the white hole now. The redshifted universe is behind us. Okay, so this is the general picture. The conclusion of the matter is that Hawking radiation diverges at the inner horizon. And this happens for this case, which was a Reissner-Nordstrom black hole, but it also happens for rotating black holes and in the inflationary Kasner model as well. So just one more thing I want to point out is that you can do this with other black hole models if you'd like. So two projects that I've been focused on, one of them is with non-singular cores. So during my PhD, there was a work that came out where people proposed a type of black hole that managed to avoid the classical mass inflation instability. So they made this inner horizon an inflection point in the horizon function. And so instead of diverging at r equals 0, the horizon function remains finite. And this is a nice potential solution, because that would mean we don't have to deal with singularities and higher order quantum gravity. We can do everything with semi-classical physics. But what I found is that it doesn't really work out. And this was additionally propped up by Roy Kerr himself recently published a paper questioning the concept of singularities in the first place and claiming that his own solution provided a counterexample to the singularity theorem. And I don't want to get too much into that, but the basic idea is that a lot of people in the field want black holes not to have singularities. They want to have some regular core in them so that everything behaves nicely. But what I found is that Hawking radiation, even in this model, diverges. And no matter what model that you throw at it, semi-classically always acts to restore sanity or destroy your hopes and dreams if you want wormholes. And then the second project that I've been working on with student Dave Yanni, who's in the room here, is to work with models with cosmological constants. So anti-de Sitter and de Sitter black holes are of interest because when you reach that inner horizon, you actually are seeing the end of the universe. But in our real universe, it's not asymptotically flat. It is expanding over time. And so we might expect that to make a difference. And so we've been looking at what the Hawking radiation looks like in these sorts of models. Okay, so we've reached the end. Here is the summary of the semi-classical part of what we have learned, which is that the Kerr metric is not semi-classically self-consistent. If you are using the Kerr metric for calculations, then you should know that this inner horizon actually gets replaced with something else. But what we found is that there is a globally self-consistent model that semi-classically predicts that you will end up seeing a singularity here, because just about everything that we would calculate, vacuum polarization, the energy of the quantum field, Hawking radiation, it all diverges and produces a space-like singularity at the inner horizon. Now you might ask, what happens after this collapse regime? So just like if you take a string and you decrease its length to 0, we know that decreasing length of the string increases its pitch. If you put your finger on a fretboard, then the frequency increases. But We also know that would imply that if you decrease the length to 0, you would get an infinite pitch, infinite energy. Of course, this isn't actually a problem, because if you take that limit L to 0, then strings don't behave like strings anymore. They behave like individual molecules which move around, and so we need new physics to describe that. And in the same way, we need new physics to describe this. And so I'll revert any questions related to that to, you can ask Andrew in a few years what his string theory predicts. Okay, I think that's about all that I have. So let me just conclude then with some acknowledgments. So first of all, I want to thank Free Food. You've kept me going throughout my entire graduate school career. I also want to thank Andrew. He's been an incredible supportive advisor, one of the most highly advocating advisors that I've come across. And you've been just a constant source of hope and intelligence throughout my career. And also thank you to my thesis committee members for taking the time every day to read part of my thesis at least. And thank you also to all of the staff in physics and JILA as well. I think there's a lot of gratitude that goes undeserved. That I've been very fortunate to have worked with you guys in helping me teach and all the other things that I've done throughout my time here. And also the community of friends that I've established along the way. So all of the fellow students that I've met in my cohort, that I've met through the Grand Canonical Ensemble, all of the great musicians that are here, and through CU Prime and the other student groups. You guys have been a great source of support. And then also all the friends that I've made in the Graduate Christian Fellowship. You've been a true community of life-giving people that have helped me to just a constant reminder that, yeah, just that the true value and purpose that I have is not inherently rooted in academia's false promises of meritocracy. Okay, so with that, I'll thank you all for attending here today and happy to take any questions.
Up to questions from the audience.
Yeah.
Want to ask about what you mean by the negative that I was saying, right? Any way to imagine that now come with a positive
That's a good question. Yeah, you're asking about what negative temperature really means. And I do get asked that a lot because I think it means a lot of different things for a lot of different people. And we have to be clear what exactly we're talking about here. So for a lot of people, astronomers included, negative temperature means you have some sort of population inversion in your system. So you have a case where the excited state is more populated than the ground state. And so you can define that as just a negative temperature that gives rise to these OH megamasers and things like that. That probably is not what we're talking about here, because really, when I was referring to negative temperature, it was related to this black body spectrum. And so if you just plug in a negative temperature to that, then you find that means it's an ultraviolet divergent spectrum. And when we did the actual numerical calculation, then we showed that it isn't actually ultraviolet divergent, but it does sort of follow that shape for most of it. So really, I would think of negative temperature just as a really high energy version of temperature. So things are blue shifted. You could also think in terms of, so we think of Hawking radiation as spaghettifying tidal forces, which are pulling apart particles at the event horizon. In this framework, you can imagine that at the inner horizon, those forces are pancakeifying. And so that gives rise to this opposite sign that the particles still exist, are still created, even though the tidal forces are acting in the opposite direction. Oh, yeah. Yeah, it probably is related to entropy in very intimate ways. And I am not the expert on that, but many others in the room are. And yeah, I think that's about all I can say with that. Probably. I'm imagining that there should be a way to calculate energy or entropy and that sort of thing in these models at the inner horizon, but that goes a bit beyond what I'm doing. Yeah. Yeah. What's the reason of including white holes in the calculations? What specifically are you? Right. Yeah, so I guess maybe like when we're thinking of this sort of thing. Yeah, so the white hole is the thing that we would see right here, and I guess you could put it right here as well. The reason I'm including it is because the math predicts that's something that you can do with the equations of general relativity, and it looks cool. But what we've seen is that when you pass this inner horizon, everything beyond that is just impossible. So even though it looks cool and it might be nice to have wormholes and white holes, I think in reality, the conclusion is they don't actually happen. Yep. Yeah, Bryce. Yep, yeah. So you're mentioning gravity is renormalizable. And so if I go back to that slide, yeah, that is a perfect question, because it's part of the reason why people say that gravity is incompatible with quantum mechanics is because if you try to do this renormalization process, you end up at each higher order, you need more and more renormalization constants that go to more and more higher orders. And so it's just an infinite chain of regress that never ends. And so you can't actually renormalize it to create an ultraviolet complete theory. But you can use it, and that's the thing that people have been working on through these past decades, is to find a way to find a complete effective field theory that's valid up to some energy scale. And so for us, this energy scale is above the unification of the standard model. And so any physics that we're used to in this universe happens in this one loop semi-classical limit. So yeah, great question. I think we should probably wrap things up soon. So maybe one final question. I'll defer to the chair though.
Why is that? Why is overall?
Yeah, great question. So why does the Hawking radiation make it so that wormholes can't exist? I guess it's essentially the idea that Hawking radiation is just a matter or radiation which is produced from a quantum field, which is initially in a vacuum state, but just particles get spontaneously produced. Those particles have gravity of their own, and that gravity pulls things inward. Usually that's negligible when people are doing simulations. You just ignored self-gravity from accreted matter. But once they get close enough to the inner horizon, then they diverge in energy, and so does their gravity. And so essentially, if you are trying to cross the inner horizon, even just one particle which is produced spontaneously is just going to suck you in and crush you into a singularity. So that is the idea, is that this infinite divergence causes the space-time to back react and collapse. Yeah.